Hi, Chris Kuzmal here. Today we're going to talk about proofs in logic. When we make a proof, there's two fundamental kinds of proofs that exist. One is described as linear reasoning, for which we're going to need to understand what a schema is, and for which we're going to need to understand what rules of inference are. And then we're going to want to understand hypothetical reasoning, which use structured proofs, which are also known as subproofs, which have three components. One is assumptions, the second is linear reasoning, and the third is how we use the results of a structured proof. First, we're going to define what provable is, though, and it's a fancy phrase that it's a finite sequence of steps using the rules of the inference to generate the conclusions from the premises, where each step preserves entailment. This is lovely. Let's look at a couple of examples. Here's an example of a proof where we say P implies Q, and we say P, and therefore we conclude Q. It's a very simple proof, intuitively obvious, but it's lacking a little bit of the formality and structure that we would like. Another example is very similar. We have the logical sentence Q or R implies Q, and we also assume Q or R, and we're able to conclude Q. We start to see that this way of doing this proof kind of generalizes. Another example we have if P implies Q and R. And we also assume P, and we conclude Q and R. We start to see a pattern where P corresponds to anything. A triangle is sort of what we put there to abstractify or to abstract things. The right-hand side of the implication operator also can be replaced. And so this sort of corresponds to a rule. And because formal logic doesn't typically use colors and shapes, we replace these with Greek letters for the triangles as well as the rectangles. So ultimately, we have a generalized form of a proof where any logical sentence, psi implying theta, and given psi allows us to conclude theta. So those fancy Greek letters are placeholders for any logical expression, and they're called metavariables. And that's what a metavariable is. Having seen it in use, understanding the metavariable hopefully is a little bit easier. Now, the structure of a proof involves using rules for how to move from one step to the next. And those rules are made up of schema, which are expressions satisfying the grammatical rules, except they may also contain metavariables. And that's exactly what we were seeing a moment ago. Each line on this example is actually a schema. And in addition to the schema, you put those rules of inference together, which is fundamentally what that whole proof was looking like, which is a pattern that includes a set of schemas corresponding to the premises, a demarcation such as a line, and a set of schema corresponding to the conclusions. And so what we'll see here is the rule for implication elimination pretty much matches exactly what we came up with before, but we formalized the structure of it so that we feel comfortable using it in a formal proof and in formal logic. Here is a formal proof. Parts 1, 2, and 3 are premises. We assume P implies Q, and then we assume what's on line 3 there, which I'll try and read for you. P implies Q implies R. And then we can use the rule we have here on 3 successive occasions, applying the rule for parts 2 and 1 to conclude Q, using the rule on parts 3 and 2 to conclude Q implies R, and then using what we've concluded from steps 4 and 5 to conclude R. And that's a proof, and that's an introduction to proofs in formal logic.